Right. Good morning, everyone. So this is stop last week, and we had to discuss how to prepare a standard solution. So I think we discussed about the calculation and the procedure, the steps involved. We had to discuss today. But anyway, I'll quickly tell uh, how to find the exact mass of NaOH required to prepare this solution. Look at the screen, students. The mass of NaOH required. Now we are going to prepare what solution? Sodium hydroxide solution with definite concentration, or we call it non-concentration. What is a standard solution? Standard solution is the one with where the concentration is accurately known. Okay, so if you can put an arrow and write solution where the concentration is accurately known. Concentration is accurately known. Accurately known. Concentration is accurately known. If you know the concentration accurately, we call it what solution? A standard solution. A standard solution. If concentration is accurately known. So the required concentration, what is the required accurately known concentration we require here? That is 0.1. And the volume 250. So this is the concentration is known. Accurately known concentration is this much. And the volume is 250. To prepare this solution, we have to find what mass of NaOH should be dissolved here. How many grams of NaOH should be dissolved here? Look at here. How many grams of NaOH? What is the NaOH mass that must be dissolved in 250 volumetric flask to prepare this solution? The mass of NaOH. Right. We know the concentration. What is the volume of this? It's 250. Since we are going to prepare 250 solution, we need to use 250 ml volumetric flask. This is 250 ml volumetric flask. Volumetric flask, not just normal flask. And there's a ring here. When you fill the solution up to this mark, it occupies exactly 250. And the other one, concentration required. What would be the concentration after preparation of this solution? Solution concentration has to be 0.1 mole per cubic decimeter. 0.1 mole per cubic decimeter. Now, to prepare the solution, students, so first we have to do a calculation and find the mass of NaOH required. So first, you have to use this equation, C equals NOV. Look at the screen. C equals NOV. Concentration is, students, known. C is known. And number of moles we don't know, but volume is known. Volume and concentration is known. What's that? Volume and concentration is known. Therefore, N equal CV. What is N equal? CV. N equal CV. What is C here? 0.1 mole per cubic decimeter. And the volume, you have got 0.25 dm3. dm3. The reason, because 250 volume, we had to convert it to cubic decimeter. How to convert 250 into cubic decimeter? 250 divided by 1000 equals 0.25 dm3. If you want, you can write down. Because volume, we have to convert it to decimeter cube, because concentration also given in per cubic decimeter. After that, you get the number of moles of dm minus 3 and dm3 students get cancelled. dm minus 3 and dm3 get cancelled. Then you get the number of moles, you get what? 0.025 moles. So this is the first step. First, you have to calculate the number of moles using C equals N over V, N equals CV, and apply the values to the equation and get the final answer. After that, students, you have to convert moles into mass. How to do that? What is the grade 10? You learn the equation. Now we know the number of moles. So we have to convert moles into mass. How? Simple N equal simple M over capital M. Grade 10. You learn this under grade. Now here we have found the number of moles 0.025 moles non molar mass of NaOH. Also, we can find total. What is the total NaOH, students? NaOH, the total they have given within bracket sodium 23. Last week also I did this, right? The second time I am doing this because since this part is bit important, you can not on the preparation of solution, you can get this calculation separately in your paper. Find the moles and concentrate. So you get total 40. So what is the molar mass of NH? 40 grams per mole. 40 grams per mole. 40 grams per mole. Now, number of moles equal what? Number of moles equal, sorry, we have to find mass, not the moles. So the unknown one is M. So I'll make the subject simple M. You take capital M into the other side, students. Moles multiplied by molar mass. Grade 10 under chapter 7, you have done it. How to convert moles into mass? Multiplied by moles multiplied by molar mass. Now moles we found from the previous one. What is how many moles we found? 0.025. We found it, right? 0.025. Right. And molar mass, we've got the total NaOH. What is the total NaOH? 40 grams per mole. So mole per mole get cancelled, students. Mole per mole get cancelled. And you get the final answer in grams. How many grams? I think last week we found, right? Can you reply on chat? How many grams? When you multiply this, you get 1 gram, right? Isn't it? Is that 1 gram? Yeah, it's 1 gram, right? Yeah, it's 1 gram. So now we can deserve how many grams? Now we found the mass. We need how many grams? 1 gram of NaOH. We have to, can you see the parts here? What is this? This glass funnel. Okay, look at the screen, everyone. This is glass funnel. What is this? Glass funnel. Glass funnel. Glass funnel, right? What is this flask? What is? Volumetric flask, right? I have given them separately at the bottom, but just volumetric flask. Volumetric flask. And volumetric flask. But there are different type of flasks in the lab. Flat bottom flask, round bottom flask. But this has to be definitely volumetric flask. Volumetric flask also available different volume, students. Different volume available. So this has to be a 250 ml volumetric flask. This should be 250 ml volumetric flask. Then you need wash bottle. What is this called? Wash bottle. Wash bottle. And this is the wash glass. Wash glass. Wash glass. Right. Wash glass, wash bottle, glass funnel, volumetric flask. So what is present inside the, inside the wash bottle, what is present? Distilled water, deionized water, distilled water. So this is how it's done. Because through the narrow neck, you can't transfer this NaOH 1 gram. That's why we need the funnel. And you have to dissolve that using distilled water. And this is the 250 mark. That also very important. I put there's a mark on the neck of the flask, that is 250 ml mark, 250 mark. So when you fill the solution up to this mark, it occupies exactly 250. Then the concentration, you get that 0.1. So remember, students, there's no instrument in the lab to measure concentration. What is available, NaOH, solid NaOH available, so you have to weigh and dissolve to get the required concentration. So this is the calculation, and when you are filling the solution up to the 250 mark, finally, this meniscus, your eye level should align with the bottom of the meniscus. That also important. If you can highlight that also, this is the meniscus. This is your eye level. Right? Eye level should align with the meniscus. Got it? Meniscus. Right. Now materials required. Shall I raise the screen? Did everyone finish copying down? The last week also I told this, but second time I reminded this today because that calculation is sweet. Because what happened? If calculation go wrong, students, definitely you get the wrong concentration. Solution prepared is wrong because you don't get the required concentration. And sometimes what happened? You weigh 1 gram. What is the balance used for this? It's triple beam balance. So electronic balance can be used. And even though you weigh exactly, you can do the calculation also perfectly correct. And you measure 1 gram accurately, that also done properly. But when you are dissolving this in the flask, sometimes you may spill some out of this funnel, or if you have not transferred 1 gram completely to the flask, then what will happen? Calculation correct. You have measured 1 gram accurate, but you have not transferred that completely to the flask. Sometimes when you're in a hurry, when you're doing this, some crystals might go out of the flask or spill. If you spill that on the floor a few grams, then what happened? You get the concentration prepared will be lower than the expected value. It's like a negative error. Negative error. Or if you had too much water also, what happened? Concentration become lower than the required amount. So those are the errors that could arise during this practical. Personal errors can occur. Instrumental errors also can occur. Like, if the balance is wrong, there's a problem with the balance. Then you can't measure this accurately. Those issues also there. Determine errors, indeterminate errors is also there. And this also you are done. Like 250, you can't measure separately and transfer. That is wrong. You can't measure 250 separately and transfer using a pipette or something. Because uh, sometimes a certain amount of drops or the liquid can retain on the pipette or the beaker. Therefore, the best thing is transfer 1 gram accurately to the flask and dissolve it in a small amount of water. And then top up the solution up to 250 mark and shake the flask at the end after closing the lid. That's the correct technique. I don't know how many of you have done this. Please raise hand those who have done this practical in school. You are supposed to do this in the school lab as a practical. How many of you have done this in the school as a practical? Raise hand. With two students. Others couldn't do this. Right. Anyway. Now, you are supposed to do this as a practical school. Remember that, right? So they encourage teachers to do it. Then only at least you should know. I don't know if you have seen these equipments, glasswares. That's then also at least that important teacher demonstration. If you are not preparing this solution in the school as a group or individually, at least teacher demonstration is important. Right. Okay, shall I read the screen? Anyone still copy now? Raise hand. Done, right? Anyone still copy now? No. Right, done. Okay. So I'll read the screen. Then materials required, students. Right, look at the screen. Capital A, watch class. Capital A, watch class. What is B here? Yeah, can you do can you label the parts? I'll give you 2 minutes. Reply on chat once you're done. When you're done, reply at least A, B, C, D, the first 5 parts. What is B here, students? B is triple beam balance. Watch class. Then what is the B here? Triple beam balance. What is C here? Glass funnel. What is D here? Wash bottle. If you only can put an arrow inside the wash bottle, what is present? Distill water. You can't use tap water for the preparation of solution, okay? Use what? Tap water contain minerals. Distill water. Use distilled water for the preparation of solution. Next one is volumetric flask. That is the most important one. Can you see there's a ring here? That's the 250 mark. This is a 250 ml flask, 250 ml mark. That means when you fill the solution up to this mark, it occupies 250. There's a lid also for this flask. Lid. Don't mix up this with flat bottom flask, round bottom flask, and titration flask. What are the other flasks? Conical flask. Titration flask. Flat bottom flask. Round bottom flask. But we don't use either one of them for this practical. We need exactly volumetric flask. In Sinhala we call it Parimamithika flask. Round bottom is Vatadi flask. Flat bottom is Pathaliadi flask. Titration flask means Anumapana flask. Conical flask means Ketuka flask. So there are different type of flasks in the laboratory, students. Be careful. You can get MCQ. So why did I mention those? You should know the names of the other flask also, but they are not suitable for this. Why? They can ask MCQs like this. Which of the following type of flask is more suitable for the preparation of solutions? You can get all the paper MCQs. Which of the following flask can be used for the preparation of solution? Huh? They can give one answer. What? Titration flask. And write in your writing book. flask, different type of flask available in the lab. Conical flask, titration flask, round bottom flask, round bottom flask, and the other one, flat bottom flask. These are the different types of flask available in the lab. But you can't use any of this to prepare this solution. Which flask is used? Huh? Volumetric flask. Because they can mix up that with the other flask and ask MCQs in the paper, right? Right. Now you can write just funnel for this. Okay. You have to use glass funnel. Glass funnel. You can't use a plastic funnel for this. Plastic funnel corrode. Remember, students, NaOH, plastic can get corroded by NaOH sometimes. And glass funnel is used normally. Plastic funnel also can, but normally we use glass funnel. Contamination. And the other thing is before that, what? All the glasswares you have to clean. And clean and dry. That was your why. If someone has used watch glass to measure HCl, like maybe not HCl, say some other copper sulfate or something, or potassium permanganate, and not clean properly, then contamination can take place. Even volumetric flask, they might have prepared some other solution, HCl. Now, when you prepare NaOH, what happens? If they are not clean it properly, they also have not clean after their practical. You also not clean before your practical. If you have used this before, you know, you clean it. But the same flask used by many people in the school, right? When they come to the laboratory. Therefore, who knows whether they have clean it or not? Therefore, you have to make sure you also better wash that with water. Distilled water is better before the practical. Otherwise, what happens? Previous batch or previous group prepared HCl. Now you are going to dissolve NaOH. What happened? There can be a reaction inside. Hydrochloric acid HCl, it reacts with base, sodium hydroxide, giving sodium chloride and water. So those are the issues. It's not that easy to tell, but when you're going to do it, it's more complicated. Many things like that. It's easy to tell. Practicals is easy to tell. It's easy to describe on the board or the screen. But when you're going to do it in the laboratory, you will learn and develop many skills. And the techniques. Now this time oral paper, they ask many practical related questions. Activity related questions. Structured essay paper also they ask. Essay type also they ask. Many practical related questions. Now there are some optional ones also, students. Now remember, these ones are optional. Look at it. Measuring cylinder also optional, right? Not only main. Because since it is 250 ml flask, measuring cylinder are not necessary. Measuring cylinder. All these are for measuring volume. What is this, student? Burette. They are optional, not necessary. Option. Burette. Oh, sorry, not burette. That is pipette. Pipette. This is pipette. Bulb pipette. This is burette. What is the last one? Electronic balance. That is very easy to handle than the triple beam balance. Electronic balance also accepted in the exam. Instead of triple beam balance. Instead of triple beam balance. What is this called? Electronic balance. Electronic balance. Right. Why these ones are these parts? Sometimes if you don't have a triple beam balance, you can use a electronic balance to measure 1 gram of NaOH. Now imagine a situation you don't have 250 ml flask, right? You don't have a 250 ml flask. Instead, you have 500 ml flask, or you don't have. Uh, I mean, sometimes you have to prepare the solution in a separate beaker. You don't have the volumetric flask at all. You have only beakers in your school. No volumetric flask. Then you can't. It's easy for the teachers and the students. We can't do the practical. Volumetric flask is not there in our lab. But if you really want to do this, you can try this with this. What? You can measure 250 ml using measuring cylinder or pipette and do it. And you can prepare the solution in a beaker, but it's not 100% accurate, but somehow you can prepare it. That's why they are option. I don't know whether you have seen them in the school laboratory. Pipette, burette, and like right. Anyway, so but 1 to 5, the dotted line ones you have to remember. The next one is procedure. Look at the screen, procedure. So what is the procedure? The main steps involved. Right. First part. Measure 1 gram of NaOH accurately using what? Triple beam balance. That is the first step. But measure 1 gram of NaOH. Obey 1 gram of solute. I put just solute. What is solute here? Within bracket I write 1 gram NaOH. For this practical we got 1 gram NaOH accurately using what balance? Using triple beam balance. In single we call it Tedandu Tulawa. Okay. So for that you need what? Watch glass as well. Because you can't directly transfer NaOH to the balance because the balance will corrode. I have given more space, right? Using triple beam balance or electronic balance. Using triple beam balance or electronic balance. In the exam, only write both this, you can write only triple beam balance enough. Step 2. Now you have to transfer the solute measured. Transfer the solute completely into the volumetric flask. Completely into the flask. Transfer the solute completely into the flask. Transfer the solute completely into the flask. Transfer the solute completely into the flask using what? should be transfer, right? Transfer. Or add. Add the solute completely into the flask. Flask means volumetric flask, okay? Using what? What do you need? What else you need to do this? To transfer this? You can't transfer directly from the watch glass to the narrowed neck. You need the glass funnel. Using glass funnel and wash bottle. Using glass funnel and wash bottle. That's why there was a one in front of the calculation. There was a diagram. No, there you saw that, right? Glass funnel and wash bottle. It's not necessary to mention those two, but it's better. Then number 3. So you have to dissolve the solute completely. Dissolve the solute completely. Dissolve the solute completely. By adding what? By filling 2/3 of the flask with distilled water. By filling 2/3 of the flask with distilled water. With distilled water. So you have to dissolve the solute completely. You should not add the water, like you should not top up the solution. You should not adjust the level of the solution up to 250 mark straight away, because then you will not have enough space, enough room to shake the solution. Even when making a plain tea or ice coffee or milk tea or whatever the fruit juice, first you add sugar, salt and everything and little bit of water and dissolve everything, right? After that only you adjust the final volume by adding water. Something like that. Same procedure you follow if you're going to make a drink. After dissolving, what happened? Adjust the level of the solution up to 250 mark. Adjust the final volume. Adjust the final volume by adding distilled water. Up to 250 mark. Adjust the final volume up to 250 ml. By adding what? Distilled water, okay? Then close the lid and shake well. Close the lid of the flask and shake well. There's a lid for the flask, right? Close the lid of the flask and shake well. Because when you do these practical students, you will put this into practice in your day-to-day life also. I'll give one example. Any students also have done these practicals properly in school, especially if they have done A-level science or university science degree, they never forget to close the lid of a bottle after opening. Others will forget. They open the lid to take sugar or milk or whatever the milk powder and they forget to close it. The next time when they come, the ants full of ants inside the bottle. Either they don't close it at all or they don't close it properly. One bad practice. I don't think any students run science practicals, they will never miss this. Second one, many people, when they open the door, but they forget to close the door. Sometimes air conditioned room, bathroom, toilets. They open the door when they come out, but they don't close it. Number 3, they on the lights, but they forget to off it. They on the fans, but they forget to off it. You might have experienced this in your house. Then parents or someone should tell, oh, you have not off the fan, you have not off the light. So that reflects you have not done practicals properly. So remember students, in the laboratory, if you open the lid of something, when you finish it, you have to off it. You have to close it, close the lid. Something like that. And laboratory glasswares, after the practical, you have to clean it again before you leave the lab. You have to clean the place before you leave the lab. So those students, they never leave the glass or the mug or the cup or the plate after eating. They want to wash it by themselves. They don't need a separate person to do it. Even they don't let the housemaid to do it. They have got used to that. That is good practices that you take home from the school. So that is reflected when you do this in your day-to-day life. I have this experience. I have this experience with students as well as with adults. If it is a hotel, no problem. But at home, you have to do this. Before you go to the bed, if the bed sheet fold, like, arrange properly pillows and the bed sheet, but when you get up in the morning, you should know how to arrange the bed sheet again properly. So don't leave that someone else to do it. Why don't you arrange your bed? Remember that. When you get up from the table, dining table, you have to clean it. So that's how the other countries that the students learn. Especially one of the best examples, Japan. There are no servants, even to wash toilets, even in the primary. That's why we are used to say Japanese hapana. Japanese hapana. That's a single term. Japana hapana. They are very skillful. Our people are lazy. I'm not telling everyone. Right. Anyway. Okay, so that's good. And even sometimes I have seen this. Now, when you open the lid of the flask, students, look at this. These are the skills you should develop when you're doing a practical. When you're learning any subject, knowledge only useless. You need what? Attitude and the skill also matters. Imagine you have a lid here. So to transfer, you have to open the lid. When you open the lid, what happened? Many students, not forget about now. If you sometimes you might say we are not doing practicals, we are not done the practicals, teachers not doing the practical manual. But anyway, if you even at home, when you open the lid of a bottle or lid of the flask, how to keep that lid? You have to keep it what? Upright or inward. Like you have to keep this like this on the table, like this, students. Lid. Otherwise, what happen? Contamination can occur. You have to keep the lid like this. That turn up. Otherwise, what happen? The chemicals can contact with the table. And the germs on the table also can contact with the lid. And when you mix the solution, that also get dissolved. Flies, they transfer a lot of germs to the surface of the tile or whatever the floor or the table. So you should not let the lid to contact with those germs. And even the spoon, no, whatever you use, fork, cutlery. So you have to be careful. These are the good practices you bring home to the kitchen. Right. And after the practical, you have to wash your hands. You have to clean your hands. You have to clean the laboratory glasswares as well as you have to clean your hand also before you leave the laboratory. We have that same practice in the kitchen. After eating, after preparation of food, you have to clean your hands. Before that also you have to clean. Right. Anyway, so the other safety precautions I don't have time to tell, but these are the skills you develop when you're doing a practical. Right. Science is full of experiments. Science is not a subject like history, remember that. And you get 25% of the questions or all level paper from practicals. Now, this time also out of all the 9 subjects, you can ask any student, those who have done this time all level exam, they tell hardest subject science. The hardest one was science. The reason they have not done the practicals properly. And the other one, they have just memorized the content of the textbook or they're not, teachers not, they are not motivated. They are not used to think out of the box. To thinking ability is less. Critical thinking And that problem solving analysis of data and all, they have not even, yeah, practice or not well trained. That's the reason. They expect the same thing, but they have learned, memorized in the exam. You know, obviously science is going to be hard. Right. So after closing the lid, and you have to shake well. And that is because you just feel, because same thing we do know before we offer to the drink to the guest or whoever. So again, we mix that with a spoon, right? Or we there are stir like the maybe a straw or something, right? Even in a drink, we do this. Before drinking also we mix to make it homogeneous. Otherwise, particles can settle at the bottom, right? So this is a solid liquid homogeneous mixture, right? Okay. Last one, you can write label the solution prepared. Label the solution prepared. What should be label included on the label? Label the solution prepared, indicating what? That means you have to put a label here. On the flask, you have to put a label. So you can make this is the label of the flask. Indicating what? Label the solution prepared, indicating what? What should be indicated on the label? Indicating the name of the solution. Yes. Name the label the solution prepared, indicating name of the solution. What else? Name of the solution. Then composition or the concentration of the solution. And date of preparation. Date of preparation. Because otherwise, who knows what it is? So sometimes the next day or after your practical, the next period, if some other group come, they will remove this and wash the flask and take that for you, they are practical. So name is here in NaOH. Composition means, students, concentration, what is that? 0.1 mole per cubic decimeter. Date of preparation, you can write, say, example 24th May 2024, like that. The prep date. Those things should be included on the label, right? Is that clear? Okay. Is volumetric flask. Done. No need to memorize. Just remember the order. First, you have to weigh the mass accurately. Then you have to transfer it completely. Then you have to dissolve it using a small amount of water, 2/3 of the glass. And then you have to adjust the level of, up to the final volume. And you have to close the lid and shake well and label it. That's it. One more thing. This solution is what? NaOH solution prepared is what? Homogeneous or heterogeneous? Can you tell me? Sodium hydroxide is an ionic compound. Can you put a stand, write it, students, here? NaOH is an ionic compound. Sodium hydroxide is an ionic compound. And completely soluble in water. And completely dissolved in water. It completely dissolved in water. Therefore, it is a what? The solution prepared is what? It is a solid liquid. Sodium hydroxide is a solid. What is a liquid? Solid liquid what mixture? If it is completely soluble in water, students, it is a solid liquid what mixture? Homogeneous or heterogeneous? Homogeneous mixture. Very good. Solid liquid. It is a solid liquid homogeneous mixture. It is a solid liquid homogeneous mixture. Now, students, I am planning to start grade 11. I mean, not grade 11, grade 10 paper class from June first week. Now, Your paper class is on Sunday morning. Your paper class is Sunday morning, 5:30. But the grade 10 new batch, that is next after your batch 2025 or batch paper class, I'm planning to start on Saturday morning after your theory class around 8:30. So 8:30 to 10:30 from next month. That means from June. If you really want to revise grade 10 lessons from the beginning, you may join that. And you have to send me a request if you want to join. Right? Because you are getting nearly 50% from the grade 10 syllabus for your oral paper. Therefore, if you have missed any grade 10 lessons, you better join the grade 10 paper class on Saturday morning. Or if you want, you can get the recording also. Right. Then next one, students, so I'll finish. So there are some video clips also for this practical. I don't know because only 2 students raise hand for this. Now not polar, like it's ionic. Sanuka in which is an ionic compound. Is when something is highly polar, it's going to be ionic. The extreme end of polar nature is what? Ionic. That means is polar means slightly positive and slightly negative. Ionic means completely positive and completely negative. Na plus, Cl minus, not delta plus. Delta means slightly positive. Okay. Quickly copy down the students. At the bottom I put a stand, write it, and the other one is remember the students when dissolved in NaOH. Yeah, NaOH is inorganic. Yes, ionic and NaOH is inorganic compound because no carbon. Yeah, obviously. NaOH is inorganic. Yes, solid. NaOH is a strong base. What are the other things to remember about NaOH? A strong base. Strong base. Alkali and as well as alkali. What is alkali? Bases that dissolved in water called alkali. And as well as it is ionic solid. Plus it is inorganic. Inorganic compound. Inorganic. Inorganic means no carbon. Organic means with carbon. And this one no carbon. Therefore it is inorganic. And no carbon means inorganic. With carbon, organic. With carbon, organic. Without carbon, inorganic. Right. Quickly copy down all the students. And one more thing I wanted to notice. When you dissolve NaOH in water, the heat is evolved. Therefore, it is an exothermic. Right? Can write that also additional point. When dissolving NaOH in water, heat is released. Heat is evolved. Heat is released to the surrounding. That means the beaker or the flask gets slightly warm. Can write that also in your writing book if you know space here. When dissolved in NaOH in water, heat is released. Or in other words, temperature of the solution increase. Therefore, it is an exothermic process. Exo means out. Thermal means heat. Heat is released. It is an exothermic process. What is exothermic? Dissolving of NaOH in water is exothermic. Exothermic. And it is a strong base. And pH value is above 7. Because I am giving many other information students. They don't, if you get a question from this in the exam, they don't ask the same thing given in the textbook. They can ask the other related questions also related to the, yeah. Okay, anyone still writing, raise hand, done, right? Shall I read the screen? If anyone still writing, please raise the hand. Additional point also you have to note down. Right. The next one, I'll read the screen. Next on the last part of the lesson, student, that is the most important part of this lesson, student, because you get essay type questions from this section. Essay type questions. Oral paper essays. from this section, the last part of the lesson. So remember now, first you learn about this lesson: mixtures, homogeneous, heterogeneous. So polar solvent, non-polar solvent, organic solvent, inorganic solvent, solubility, right? Then composition of mixtures, right? Mass fraction, volume fraction, mole fraction, concentration, like that. And then you learn preparation of solution and solubility. Factors affecting solubility also you learn. And then preparation of solution. And wait, this is for practical also for the previous one. Wait, I'll show that quickly. Look at this. I'll play the video, you can watch. Now this is, they do this using a, this is also a way of doing it. You can watch the video. I'll play this.
We now need to add the calculated amount of potassium dichromate to the beaker. In this case, it was 2.94 gram. Record this in your data table. We may now turn the balance off and remove the beaker. To make the solution, we will now add approximately 50 milliliters of water to the beaker. And stir the mixture to dissolve the solid. When the solid is completely dissolved, we may now transfer the solution to the volumetric flask. We will use a funnel to transfer the solution. And rinse the glass rod and beaker into the funnel. This is complete transfer of the solution into the volumetric flask. So rinse the funnel into the flask, remove the funnel, and if the solid has not completely dissolved, you may agitate the flask. We can now add water to the flask to a point just below the volumetric line. To have exactly 100 milliliters, the meniscus of the solution must be on the volumetric line of the flask. A medicine dropper will be used for this final adjustment.
I stop the video for a while. Now you can see the meniscus. So you can see this is the curve, like you can see it clearly now, students. There's a sharp curve that is called meniscus. So it's like this. Can you see here? It's like this, right? So this is the bottom of the meniscus. Your eye level should be what? Aligned with the meniscus. Bottom of this meniscus. Otherwise it's wrong. If you do like this, it's wrong. This is the 250 mark, but you fill the solution like this. That is wrong. That is wrong. This is incorrect. This is incorrect. But here the meniscus should be above the mark. Meniscus should be above the mark. This is the correct method. This is the correct one. If you want, you can show that separate, because that also they can ask in the exam. Right, okay. You can watch the rest now.
The final step is to place the stopper on the flask and invert the flask to ensure uniform concentration. We now have exactly 100 millilitres of 0.100 mole per litre potassium dichromate solution. If the measured mass had not been 2.94 gram, we would use the measured mass to calculate the actual concentration of the solution.
There's one more small one. You can watch this also if you want.
The flask up to the line. This can be done using distilled water from a wash bottle. As you get closer to the line, it's important to take great care, because if you overshoot, you'll have to start the whole thing again. When you're within a couple of centimetres of the line, make sure you're viewing at eye level and add the water very slowly in small portions until the bottom of the meniscus is touching the line. You may want to use a dropping pipette at this stage if you're a little nervous. And here you can see that the bottom of the meniscus is touching the line, so we've filled the flask to the correct level. Once the solution is made up, it should be stored with the stopper firmly in place. And before using the solution, you must ensure that it is homogeneous, which can be done by gently inverting and shaking the flask. We now have a standard solution which is ready to be used in a titration.
Right, so that's how it's done. Now, before I start this, the last part, students, separation of mixtures. We have to start. Okay, I'll continue this one today, and then next day I'll start the fourth lesson. Method of separation mixtures. Now, actually, there are 10 methods here, students. I have given here 10 different methods of separating mixtures. This year oral paper, they asked this number 7, 8, 9, 2023 oral paper they asked. They asked this under structure essay. This time oral paper, they asked this under structure essay. 2023 oral paper, they asked this under structure essay. What? Preparation of separation of mixtures. Distillation. There are 3 types of distillation. Complete the blanks. One is called simple distillation. What is simple distillation? Simple distillation. Second one is steam distillation. And last one is Fractional distillation. Fractional distillation. So these are the three types of distillation. What? Simple distillation, steam distillation, and fractional distillation. So this time oral paper, they asked this. And the last one, chromatography. Chromatography. And solvent extraction also bit important. Others, they don't ask in detail. The last 5 separation techniques, students, bit important. Because they can ask under SEDAP questions. Others are simple methods. Even we practice them in our day-to-day life also. The other methods. Mechanical separation means we mostly practice them in the kitchen. Filtration, we do, right? Coconut milk, we filter. After boiling something, we filter it. Or even when making a plain tea, tea leaves, we have to filter, right? We have to remove leaves from after putting tea leaves into hot water, boiling water, we have to filter before making the plain tea. So we call it filtration. That depends on the particle size. So in mechanical separation, what properties are considered? Physical properties based on the difference of the physical properties. Physical properties. What are the physical properties of components? Differences of the physical properties of component. Right here, physical properties of components. Based on the differences in the physical properties of components. Physical properties. What are the physical properties, student? Density, size, color, appearance, texture. These are boiling point, melting point. These are called physical properties. These are called physical properties. So example, I don't know whether you have seen this in the kitchen, like now traditional ones, modern kitchen, we call it not the kitchen, we use pantry, right? But ancient time in the past, traditional kitchen has all this, but in Sinhala we call it kulla, we know in pan. Penere. Right? Then molgaha, wangadiya. Kulla nambiliya. I don't know how many of you have heard at least this. If you have your grandma's house like in a rural area, then you will definitely, or if you go to rural areas, they usually use them. But kulla in the kitchen, the separation, all this for the separation technique. Kulla, that's for winnowing paddy and whatever the light material mix up with paddy, or the rice mixed with some other heavy particles. Kulla. Then nambilia to remove sand from rice. Penere or kirigotta. Penere and kirigotta. So sieving like. So all this what? Shifting is a mechanical method. So shifting. Then using direct into stream of water. Now sometimes what happens? When you put some seeds into water, some seeds float on water because they are not, they are damaged or like cavity inside those seeds, so something density is low. The seeds that settle at the bottom, like the good seeds. Like that was you can easily predict whether the seeds are good or not. And again, I have given based on which physical property these ones are used. Look at here. Number one, based on the differences in what? Removal of gravel from sand by sieving. Sometimes Mason bar students, to get fine sand, also they use rice or something to get fine sand from gravel, the large particles, or maybe they take river sand, can contain some wooden materials or something, then they do this what? Based on the differences in the density. No, not density, removal of gravel by saying that is based on the difference in the size of the compound. The particles with a small size passes through the filter. Even filtration, the same thing. And magnetic separation based on difference in the magnetic properties. Magnetic properties. Some substances or some components are magnetic. Some components are non-magnetic. Magnetic components get attracted to the magnet. I'll give one of the best example. Imagine heap of garbage. Garbages, you have stationary, plastic, polythene. With that, you have some metal, mineral or metals, metal pieces or steel pieces or pins or something. So instead of picking up this manually, you using hand, you can have a electromagnet. And then all the metal pieces get attracted to the magnet, but not the plastic or wood or any other material, polythene. Only metal pieces get attracted to the magnet. Then you can unload that and you can clean the place free of metals. So because metals you can recycle, right? So like that only. That is one example for magnetic separation. The previous one with the Renault blanks, right? That is based on the difference in the wait, not size is different. This will be a wait. This will be complete the blank here. Actually, this is size. This one based on the difference of the size. Here it should be density. Physical properties. I can write here physical properties within bracket like density of the component. So in front of mechanical separation, you can write based on physical properties. Based on physical properties. Within bracket, write in front of the heading. Based on physical properties. But here the first blank, you write density. Size and this is magnetic properties. Right. Density, size and magnetic properties. Okay. Next one. There is one separation technique. There are 10 separation techniques. The first one is mechanical separation. That is what we practice in our day-to-day life. Next one is, students, vaporization or evaporation. Actually, salt industry, we do this. Sugar industry, we do this. If you want to get an example within bracket, we practice this method. We use this separation technique. Preparation of what? Salt, sugar, salt industry, sugar industry, we do this. Why? We evaporate water to get the salt crystals from seawater. Sugar industry, sucrose solution of the phloem sap of sugarcane plant, the stem. We evaporate water and get the sugar crystals. Sugar industry. Yes. So these are the some of the industries where we use this. Okay. Sugar industry, salt industry. Hurry up, students. Even extraction of gold also I have given. Okay, done. Now remember, students, if gold, if for the extraction of gold also we use this. Here one letter is missing, you can add B here. B is missing here. Now, when you boil seawater or when you heat seawater due to solar heat or due to separately if you supply heat, what happened? Actually, in evaporation or vaporization, what happened? There must be a volatile component. Volatile component get evaporated and non-volatile component remain. What is volatile in seawater? What is volatile? Salt is non-volatile, student. Salt is non-volatile. Right. For the extraction of gold, we do this. Next one. Yeah. The extraction of gold and extraction of sugar also you can write. Extraction of gold we use what? Evaporation. Extraction of salt from is called salt industry. Solvents. Solvents or salt industry. Right. Then next one, filtration. Actually, this filtration, we do this at home also. Can you see this coconut milk? There's a filtration. We do this in the kitchen also. We have a filter. In Sinhala, we call it penere or something. Penere. You have holes here. Tiny holes. Like a panel. So through this, what happened? Coconut milk. Milk you can take to a bowl. Milk. What milk? Coconut milk. And the solid retains here. Solid particles of the coconut retain because solid cannot pass through the filter. Sometimes the similar one we use in the filtration of not a spoon here, like in Sinhala we call it tegot or tegot, like so into a cup. So if you have you can transfer tea leaves. So here tea leaves retain here. What is tea leaves? And you get here plain tea, like you can get here tea, you can get here the water. Solid pieces written here. So we this also we use. That's also filtration. We filter. Making milk tea also must be doing. Yeah, even not only plain tea, milk tea also. But sometimes some milk, powdered milk or milk powder, some solid particles can be left. Yeah, even when you dissolve because it's a heterogeneous mixture. That's why ice coffee, milk, coffee, fruit juice. We have to shake again or mix with a spoon or straw before drinking, right? Because with time particles settle at the bottom and it becomes a heterogeneous mixture. Even Milo packet, vanilla milk packet, you have to shake well before drinking because the content inside heterogeneous, even Tipex or correction fluid. This also like that, yeah. So there's fill. Now in the laboratory, we can't use Tegot or the Penere in the laboratory. That is in the kitchen. Filtration. But this is in the kitchen, we use a filter paper. What is used for this? A filter paper. Can you please highlight or underline this filter paper here? Filter paper is used. I'll put a cage around this. That's the most important part here, filter paper. And filter paper, there's a support here, the glass funnel. Funnel is the support for the filter paper. And then you put, say, muddy water or something. And along the glass rod, you transfer this because otherwise the filter paper can get damaged when you're pouring this directly, right? And what is left here, there are two components you get here. One is the residue. What is that called? The residue. Is one component is the residue and the other component is the filter rate that is collected at the bottom. What are the two components here? Residue and the filter rate. Residue is left on the funnel and the filter rate is transferred to the beaker, added to the conical flask. Is that clear? Hurry up. So some solutions, students, we filter like this because now here you have salt and soil. What is the residue here? Soil. Soil become the residue. And right in front of the students, what is the residue here? Soil. There are three components here. What are the three components of this mixture? Soil, water, and salt. So what will be the residue here? Residue will be soil. Soil or the sand, it will not pass to the filter paper, soil. Residue is the component left on the filter paper. And the filter rate contain what? Filter rate will be salt solution. What is the other separation technique that should be coupled with this if you want to get salt out of the salt solution, students? Can you tell me? Now I want to separate it further. Now there are three components. I separated soil particles or the sand or the soil left on the filter paper. You can write and get it if you want. Now I want to separate this further. I want to get salt. To get pure salt. To get pure salt, what should be done? Yes, can anyone suggest a method? What is the next separation technique we have to couple with this? To get pure salt from salt solution, filter rate is the salt solution. Yes? Can anyone suggest a method? Yes, students? How to do it? That's by very good. Yes, Sadhini correct. Sanuka correct. By evaporation. You can take this to evaporate in dish, and you can evaporate by evaporation. What is evaporated? Water is evaporated and pure sugar crystals left. Salt. Pure salt is left. This is called evaporating dish. Evaporating dish. What is evaporating dish? So can you mark that also? Hurry up, students. Because in the exam they can do it. Now filtration I have given here, but complete the blanks at the same time. How to do this? Filtration of impure water. Filtration of impure water. Filtration of impure water or polluted water. For the in water purification plant or polluted water. Then filtration of mixture of chemicals using what? Filter paper. Filter paper. That's what we are doing here. And next one is used to separate coconut milk from the pieces of solid coconut. What is this? Milk strainer. In single we call it kirigot. Milk strainer. Milk strain. Complete the blanks also, students. Hurry up. When you are now in the exam, they can ask labeling this figure diagram labeling. They can ask, okay, the glass rod important, filter paper important, glass funnel important. What is this flask? Actually, this flask mostly conical flask. What is this flask use? Conical flask. Now I told there are different type of flask. You don't use titration flask or volumetric flask. This should be a conical flask normally. We use a conical flask for this. A conical flask. Use what flask? A conical flask for this. Hurry up, students. Okay, enough time. Then next one, next separation technique. Since there are small practicals that you are supposed to do in school, students, they can ask them on the structure. They say crystallization. Crystallization means obtaining crystals from by evaporating solvent. Right? What is crystallization? Obtaining crystals by evaporating the volatile compound. You can write this: obtaining crystals by evaporating solvent. By evaporating solvent. Right. Obtaining crystals by evaporating solvent. That means volatile compounds evaporate. Volatile compound evaporate. Non-volatile compound remain. Example, seawater. What is volatile? Water. What is non-volatile? Salt. So what happens when you evaporate water, student? It becomes thick solution or dilute solution. Thick solution. Concentration increase. As water evaporate, concentration increase. When the concentration increase beyond a certain limit, what happens? They separate out, forming crystals. So right, when concentration of a solute exceeds the maximum possible concentration, in the solution, the solute separates out, forming crystals. So crystallization is used what? To extract what? Salt from seawater. That is called salt industry. And you can write to extract sugar, that is sucrose, from phloem sap of sugarcane plant. That is called sugar industry. That is called sugar industry. That is called sugar industry. Okay. The next one, students, so what is recrystallization? That means what? The crystals, again you dissolve. Crystals, impure crystals dissolved to get pure crystals. What is recrystallization? Impure crystals, impure means the crystals with impurities, dissolved in hot solvent and cool. But impure crystals or crystals with impurities redissolved in hot solvent. Crystals with impurities are redissolved. Look at it. Crystals with impurities are redissolved to get recrystals again, right? Are dissolved again. Dissolved in what? Hot solvent and cooling. Hot solvent and cooling to get a small sample of pure crystals. You can't get large amount of crystals from this. To get small sample of pure crystals. but you have to dissolve the impure crystals a lot. That means it should be a saturated solution. You prepare a saturated solution of impure crystals by dissolving it in hot solvent. Hot solvent, hot water or something, or any other hot solvent, alcohol or whatever, and you cool it. When you cool, what happened? Solubility drops. Why cooling? Solubility decreases when cooling. When solubility decreases, what happened? Pure crystals get deposited at the bottom. Is that clear? When cooling, pure crystals deposited at the bottom. Done? Right. Can you now, can you complete the blanks here, students? Can you quickly complete the blanks here? Right. Hurry up. Right. Okay, I'll erase the screen. Let's complete the blanks. Recrystallization. Look at it. So recrystallization, first, what is the first step? We dissolve impure solid what? Look at the screen, students. We dissolve impure solid used to separate pure substance from a mixture with impurities. From a solid mixture, right? It should be a solid mixture. From a solid mixture with impurities. So impure solid is dissolved in hot solvent. What this? Hot solvent. And I'll highlight the important ones. Hot solvent. Till it become what? Till it become saturated. Till it become saturated. Till it becomes saturated. After that, saturated means like it's a very thick solution. Otherwise, you will not be able to get crystals even when you cool it. After that, students, separation of impurities by cooling. Because it has more, if it has little amount of impurities, impurities less. Impurities will not get saturated, only the solute gets saturated by cooling the hot solution. Now I'll give one of the best example. You make a plain tea. It's very thick, not a plain tea, it's honey. You add a lot of sugar and make a plain tea. You add a lot of sugar and make a plain tea. What happened? What happened when the plain tea get cooled? Like, you know, when you offer the hot plain tea, when you offer, it's hot. But after some time, what happened when it's settled, when it's cooled down? Sugar crystals begins to appear at the bottom. Sugar crystals begins to appear at the bottom. Sugar crystals begin to appear. Yeah, something like that. You dissolve when it's hot, but when it cools down, solubility drops. Solubility of sugar crystals decrease when it cools, and they will deposit at the bottom. That's what we use here. So impure crystals of the solid is obtained by filtration of the filtrate. By filtration of the filtrate, then you can filter it. You can apply the other technique, previous technique, filtration. Get it? Filtration. You can filter it. Now you have a solution and a solid. You can filter and get the crystals, pure crystals. That's how it's done. Okay, students. Next one, solvent extraction. So the next separation technique, number 6. So how many separation techniques are there? 10. Now from number 6 onwards, bit important. Why? Because you can get them under essay type questions. These ones they can ask only for MCQ. So like, not big questions. Structure is a small part they can ask. Or they can combine more than one technique, separation technique, and ask questions. Now this is very, very important. This is called student solvent extraction. Solvent extraction means extracting a solvent using a suitable, extracting a solute using a suitable solvent. And what we use the instrument for this called separating funnel. What is called? Can you label this rightmost side figure label as separating funnel? I don't know whether you have seen this in the school. It's available in the school laboratory. Separating funnel. It's made of glass. We call it separating funnel. In Sinhala, we call it Berum Punile. Separating funnel. There's a tap here, stopcock. And then you have the lid here. Lid also available. And you can close the, from both the ends, you can close. So how to do? You can, in solvent extraction, we use a suitable solvent. Use a suitable solvent. So we have a impure solution, right? We have an impure solution. Impure in the sense like we have, say example, we have iodine or iodine in water. But we want to get iodine out of water. We want to get pure iodine from the aqueous solution. Now we use a suitable solvent. Right? We use a suitable solvent where iodine get dissolved well. Extraction of a solute using a suitable solvent. So you write there, extracting a solute from a solution, from a mixture using a suitable solvent. Using a suitable solvent. Where the solute is more soluble. Using a suitable solvent in which solute is more soluble. In which solute is more soluble. Solute is highly soluble. Solute is more soluble, or in which solute has higher solubility. In which solute has higher solubility. That means in the new solvent, it should be more soluble and it will come out from the old home and come to the new house. New house is more suitable for the solute. That's what it means, which has higher solubility. So the solute doesn't like to stay in the old house. Therefore, when there's a new comfortable place, then solute will leave the old place and come to a new place. New place is a solvent. Old one is a mixture, like a lot of other substance also. So what is used for, what is the equipment used for the students? So please write the first blank, separating funnel. What is used for this? Separating funnel. What is used for this? Separating funnel. Separating funnel is used for the solvent extraction. Plus, example I have given what? Extraction of iodine. Extraction of iodine from iodine within brackets, right? I2. So if you only write iodine is non-polar inorganic substance. Iodine is non-polar. Iodine is non-polar. Therefore, it is more soluble in what? Therefore, it is more soluble in non-polar solvent. Therefore, it is more soluble in what solvent? Non-polar solvent. More soluble in non-polar solvent than in a polar solvent. Than in a polar solvent. Right. It is more soluble in non-polar solvent than in a polar solvent. Right. Iodine is non-polar, therefore it is more soluble in non-polar solvent. Therefore, to extract what is the most suitable solvent? A non-polar solvent. Now it is in water. Can you see? Aqueous iodine solution is what? Initially iodine is in water. But it doesn't like. Why? Iodine is non-polar, water is polar. So right here. Iodine and water, iodine non-polar, water is polar. Aqueous solution. So this is yellow. Pale yellow solution. Can write here yellow. The color is yellow. Carbon tetrachloride students colorless. Colorless. Upper layer is yellow. Bottom the CCl4, right? Within that carbon tetrachloride is CCl4, right? The formula students CCl4, but it's not a good solvent to use. It's carcinogenic, even though they have given here. Nowadays we don't use this in the lab. CCl4 is non-polar. It's colorless. This is a non-polar organic solvent. What is CCl4? Non-polar organic solvent. So we use non-polar organic solvent to extract iodine from the upper layer. Now colors also important. Huh? Upper layer is yellow and the bottom layer is initially colorless. Now you shake these two layers, you mix. You close the lid of the flask and close the tap and shake well. What happens now? Now the layers mix up. You can write here bottom one, what happened? Layers mix up. Layers are mixing. Two layers mix. Two layers mix. What are the two layers? CCl4 layer and water. Two layers mix well. This is shaking. When you shake, what happened? The lid is closed, this end also closed, this end also closed, the tap also closed. Therefore, it won't go out. When you shake, what happened? Iodine gets an opportunity to enter into where? To the bottom layer. What is bottom layer? Carbon tetrachloride layer. Iodine like to stay there because both the guys having similar properties. Now iodine is where? Bottom layer. Now, at the beginning, iodine is in water. Now what happened? This become purple in color. Now what has happened, students? CCl4 layer become what? Now CCl4 contain iodine, that become purple. Earlier CCl4 layer is colorless. Look at here, I marked. Look at the screen, everyone, and label it. Huh? Don't just wait. Because just by copy down. It's easy to remember this from the figure than copy down a paragraph. That's why. CCl4 layer earlier colorless, now it has become purple. Purple. Right. After that, upper layer become what? Now upper layer become pale yellow or colorless. Earlier yellow, now it's become pale yellow. Actually, the textbook, like, it's not clear. The colors given wrong here in the textbook, because the last one, the color should be the intensity should be lower than the first one. This one dark yellow, like, and this is pale yellow or almost colorless. Why? Now, at the beginning, more iodine left in the aqueous layer. Now more iodine what? Here no iodine, here no iodine. This one more iodine. Now what has happened? Purple has more iodine. And this one has less iodine. Upper layer has less iodine. Bottom layer has more iodine. So we have extracted iodine into which solvent? What is the solvent used here, students? Carbon tetrachloride. It is non-polar. Therefore, it doesn't mix with water. Carbon tetrachloride is non-polar solvent. Therefore, it does not mix with water. Therefore, we have extracted iodine into the bottom layer, which is CCl4. Why CCl4 is settled at the bottom? Because it has high density. You can write that also. CCl4 has higher density than water. CCl4 has higher density than water. Therefore, it's settled at the bottom. Okay. Now, this is, I don't know whether you have done this practical in school. This also you are supposed to do it in the school as a practical. Right? What is capital A here? Aqueous layer. Complete the blanks for the last one. Aqueous layer. Bottom layer is what? CCl4, carbon tetrachloride layer. If you want to write the colors also. Aqueous layer is yellow. Right? CCl4 layer is colorless. But that is before. After what has happened? CCl4 layer become purple. We'll write the final color. Finally, it becomes colorless, so almost colorless, very pale. Pale color. This is purple. This iodine also like a katusa, like camouflage. Depending on the environment, color change. What is the color when you add iodine into starch, students? Iodine with starch is what? Blue, right? Dark blue or purple. Iodine in water, pale yellow. Iodine in CCl4 organic layer, purple. Iodine in Ki solution, for the starch test, the iodine solution we use in the laboratory is what? Brown. See, the iodine is like a lizard, like a katusa, like changing the color, depending on the place. Right? Camouflage. So this one, what happened? The layers, you get this layers out. I think C and D, wrong. Yeah, bottom layer, you get CCl4, you take it out. And the upper layer will be aqueous layer, water you take separately. So you can separately take the two layers out. Not to the same beaker, okay? Not to the same beaker. Right. So then there are some conditions for solvent extraction. Shall I read this? If you want, you can take a screenshot. Hurry up. Wait, there are two blanks to complete. Extraction of iodine from what? Aqueous solution. Complete the two blanks at the top. Aqueous solution to carbon tetrachloride CCl4. And iodine is non-polar and it is more soluble in what? CCl4 than in water. Iodine is non-polar. CCl4 also non-polar, and therefore non-polar mixed in non-polar. So finally, how to take pure iodine? Pure iodine can be obtained by evaporating CCl4. Can write that also. Put a stand right here. Pure iodine can be obtained. Otherwise, that also mixture. Pure iodine can be obtained by evaporating CCl4. Can be obtained by evaporating what? What? CCl4. Note down that also. You can extract pure iodine by evaporating the solvent. Now, when you did you finish copying now, students? Now, when you do solvent extraction, there are some conditions. Two solvents must be immiscible, should not mix. That is the main requirement. Otherwise, you get again a mixture. So write the conditions for solvent extraction, students. Right, two solvents must be immiscible. Or you can write what? Do not mix, must be immiscible or should not mix. should not mix. Immiscible. And substance should be more soluble in the solvent than in the original solution. That means in CCl4. What is the solvent we use here? Carbon tetrachloride. Than in water. That is the other requirement. Right? That's the other requirement. It should be more soluble in the solvent. The next one is what? Two solvents should not react with each other. What happens if carbon tetrachloride and water react? That's also a big problem. And solute should not react with the solvent. That means that iodine should not undergo any reaction with the solvent. If you only can write within bracket, but iodine should not react with CCl4. Otherwise, you will not get pure iodine. You will get something else, some other product. Iodine I2 should not react with what? Within bracket, you can write should not react with CCl4. If these conditions are satisfied, only you can apply this method. Should not react with carbon tetrachloride, CCl4. That you can write within bracket. Example. CCl4 and iodine should not react. Iodine and CCl4 and water should not react. Two solvent can write that also within bracket. Within bracket, right? For this, you can write water should not react with CCl4. Water and CCl4 should not react. Otherwise, that also will be a problem. Should not react. Should not react with each other. That also you can highlight. Two solvents should not react. Solute also should not react with either of the solvent. And two solvents must be immiscible. And iodine should be more soluble in the solvent introduced. That's it. So if these conditions are satisfied, only you can use solvent extraction. Otherwise, therefore, solvent extraction cannot be used to extract all the to separate all the mixtures. So can write applications. Examples for the application is what? Extraction of plant oil. Right here, extraction of plant oil. We can use solvent extraction. Can write one application for this. Example, you can write what? Cinnamon oil from cinnamon leaves. Cinnamon oil from cinnamon leaves. Like that. Extraction of plant oil. Sometimes we call it essential oil. Then extraction of medicinal components of plant material. Extraction of medicinal components or medicines from plant material. Extraction of medicines from plant material. We can use this. This is called essential oil. Okay. So those are some of the industrial applications. So if you get a question from this, they can ask an instance where we use this now to extract oil, plant oil, and to extract some medicines from the plant material. And here we did practical extraction of iodine from water, right, students? So next day we are going to finish this lesson. And the unit 4, I have already shared with your group. The fourth lesson, definitely I'm going to start next week, 1 hour physics and 1 hour chemistry, right? The remaining part, it won't take much time. But anyway, this oral paper, they asked distillation. Therefore, I don't think they'll ask that in your paper again. Distillation, simple, fractional, and that was a bit lengthy part. I discussed that today. Next week, I'll discuss that. Right. Okay, then students. So Sunday morning, paper class, I have shared 2 more papers. Please keep the answers ready before this Sunday morning. You will be having the class at the usual time. Paper class. Right. Okay, then stop for today. Have a good day and God bless you. We'll continue the rest next class.